So in 9.1 we talked about the geometric series and how to know if it converges. Now we're going to start talking about power series, and including in that is a geometric power series. And this is foundational to a lot of stuff that we're going to be doing moving forward in this unit. So we're just sort of laying the framework for it right now. All right. So 197 in your book is where you can find that. A power series is really, what it sounds like, right? It's a series where we're raising things to certain powers. And in this case, they're going to be variables for the most part, okay? And what we're going to do is expand on the idea of a geometric series where we were looking at mostly the common ratio being numerical. Now we're going to start looking at that common ratio as being a variable or a variable term or a variable expression. That's what makes it a geometric power series. Why that happened, I don't know. And so just note for this particular example, this is a geometric power series because what is the common ratio? X. We're multiplying by X every time. Okay. And then if it does converge, all right, so think about what we know about geometric series. If this particular series converges, what has to be true about X? Yes?
It's in between -1 and 1.
There you go. Okay. So it's the absolute value of it is less than 1, which means that it is between -1 and 1. Okay. So that's what has to be true about X in order for this series to converge. So that same idea applies. This is called the interval of convergence. And that's a phrase that we're going to use over and over again. And we hadn't really talked about it that way in 9.1, but that interval of convergence where X has to lie is going to be important. We're going to go through and find that over and over again in most of our problems. The other thing I wanted to mention, because I know we didn't go over the homework yet for 9.1, but one of the things I want you to get in the habit of is justifying your conclusions about a particular series, whether it converges or diverges, and what test you used. We're going to end up with 7 or 8 tests overall that we're going to be using, and some of the ones that we started with, geometric series test, the nth term test, are quick and easy ones to kind of use right away, but as you'll see, when we come up to a situation where it's inconclusive, we're going to have to then rely on some other test, and we'll get there, but just I wanted you to be aware of that as we work through it. Okay. Let's talk about this particular series again. We can find the sum, right? We've established that it is a geometric series, and we know that the common ratio is R. So if you recall, the sum of that particular geometric series is the first term over 1 minus R. And this is, this formula is something you definitely need to know, and we're going to use a lot. So the first term here is 1. As we've said, what is the common ratio here? X. So the sum of this particular series is 1 over 1 minus X. If I added all those terms up, believe it or not, that's what we would get. Okay? And as we're moving through this unit, we're going to be doing a lot of this, seeing this long series with all these different terms in it, and then it just equals some other relatively simple looking expression. Okay? That's going to be a common thing we're going to talk about here. All right, so here's what this means. F of x equals 1 over 1 minus x. If I wanted to write it in sigma notation or summation notation, it would just be this, okay? Now notice here that this time we started n equals 0. That will allow us to get the 1 for the first term. Okay, so the first term is still just 1 even though n starts with 0, and then I get x to the first, x to the second, x to the third, etc. Okay, so again, getting used to figuring out a way to write this in this notation is something that I think we're still getting adjusted to. All right. Now, here's that was sort of an overview, simple, basic example. All right. One of the things that you're going to be doing is you'll be given a function, and then you'll have to write it out in this form or figure out what the sum is if you can. Okay, and so that's what we're going to do on this next page. Okay, so what it's asking for is to find a power series for this function. Right, and that power series means we need to be able to write it in sigma notation. We need to express the nth term in some type of way, and then so that's what so we're gonna find 4 terms for starters. Then we're going to find the interval of convergence. We're gonna write the general term. So again, what we're really doing is converting this from function notation to power series notation. Okay. Now, this is where we get into algebraic manipulation, where it gets a little tricky. What we want is we want to turn all of these problems into some kind of form that looks like this, if we can. And if we can turn them into that form, then we know it's a geometric series. We can turn it into a power series, and we're just kind of good from there. Okay, a geometric power series. So here's where we play around algebraically a little bit. Okay. First off, if we assume that both of these are in this form, my first term for this one is just going to be 3. Okay. And then my r is just going to be 2x. So that's what I'm going to identify first. Okay. A equals 3, r equals 2x. And why that's important is because when we write the terms out, or we come up with the general term, we can start with that and work from it. And hopefully in your 9-1 homework, you start to get a sense of how that works. So if I start off with 3 as my first term, and all I'm doing every time is multiplying it by 2x. If 3 is the first term, what's the second term? 6x, right? Just multiply the first term by 2x. Now I multiply this by 2x. What do I get? 12x squared. And then I need one more term. Multiply that by 2x. 24x to the third. Okay, and so on. Right, that's how you create the power series. You take that first term, then you multiply it by the common ratio a bunch of times until you come up with whatever expression they're looking at. Okay. So here are the first 4 terms. Now we need the general term. All right. Now, that really is a matter of saying the first term times the common ratio to a power. Right. So my first term here is 3. My common ratio is 2x. All right, so the nth term, that's a sub n, that's the general term. Okay. Every time for a geometric power series or geometric series, you take the first term and you multiply it by the common ratio to the power, because whatever our power is will give us whatever term we're looking for. Now in this case, in order to get this to turn into a 1, we're going to start at n equals 0. If I start at n equals 0, then this whole thing will be 3, and so I get this first term, okay? If you wanted to start at 1, you could. Then this would change to n minus 1, okay? So just be careful with that. It's determining what you want your series term number to start with. If you want n to be 0, that's fine. If you want n to be 1, you just have to make an adjustment there, all right? And so then my sigma notation just ends up looking like that, okay? So I start at n equals 0, we go to infinity, and then I just take my nth term and I plug it in there. And so what I've been able to do, here's what we've accomplished through this, right? We've taken this function and we've expressed it as a power series in sigma notation. That's what we've accomplished. Now, sometimes you're going to see it this way first, and they'll ask you to write it as a function. Okay? Question. Now, you might be thinking to yourself, okay, this one does not look like it's in that a over 1 minus r form right now, because there's only one term over here. So how could I make 1 minus r equal 3x? Think about that. Try to come up with what the r value needs to be for this problem. And the key is we're trying to get it into this form because then we can write it as a geometric power series. So what does r have to equal here? 1 minus 3x. So what I'm going to do, what that really means is my common ratio is an expression. We're not used to thinking of a multiplier as an expression, but you're going to get used to it, trust me, because it's going to come up a lot as we move forward beyond this point, okay? So here's what I got. Oh, shoot, I guess I didn't finish that last problem. My bad. I didn't find the interval of convergence. My bad, sorry about that. Yeah, so the absolute value of 2x, since that is my common ratio, has to be less than 1, which means x has to be in between negative 1/2 and 1/2. That's my interval of convergence. Sorry, I forgot about the rest of the problem. My bad. Okay, yeah, that's important. It's literally right there at the end, and I just ignored it. Okay, back to this. Okay, as we talked about, in order for this to work, my r value, my common ratio, has to be 1 minus 3x. Now, I've rewritten it that way. And again, we went through it and solved it before I finished the last problem. Here's why this is important. What is the first term? 1, yeah. This is the first term. And so my r is 1 minus 3x. So again, I have an expression that is my common ratio. And so now we can do the same thing. So if my first term is 1, okay, I have, this is h of x. So that's 1. Then to get my next term, I have to multiply that by 1 minus 3x. So this is plus, and I'm going to put it in parentheses, because now I'm going to multiply that by 1 minus 3x again. And then I'm going to multiply that by 1 minus 3x. Again, is that 4 terms? That's 4 terms. Okay. So same idea as what we did before, but now my multiplier is an expression. And here I wrote it out. Nice and crammed it up a little bit. Like I said, in this unit, we're going to be seeing this kind of thing happen over and over and over again.
So you don't need to like expand already.
Well, it asks for the first 4 terms.
But I mean like
Oh, like to multiply it? No.
Yeah.
No, you do not need to expand it. If it can be simplified easy, fine. We're gonna see another example where we simplified a tad, but nothing like foiling it out or anything like that. Yeah, no, it's best left. But that you can clearly see that's a power series. All right, what is the nth term here? How would I write it?
1 minus 3x.
Yep. Now I think, did I know? I didn't include the 1, right? I could have. Could have put that little 1 right there for the first term, right? But obviously that doesn't do anything. But if you wanted to, you could, just to get in that habit of first term times the common ratio to the nth power. And so again, since the first term is 1, in order to ensure that this first term is 1, I'm going to start at n equals 0. So this is really what I'm going to use in my sigma notation. This time I will not forget to do the integral convergence. So this 1 minus 3x needs to be between -1 and 1. Now, and here's where we got to be a little bit careful. Okay, remember these are little ands. So my 1 minus 3x is in between -1 and 1. Now, I'm going to subtract 1 from both sides, but here's the thing where you got to be careful. I'm going to have to divide by -3, which what is that going to do to my inequalities? It's going to flip them, okay? And instead of rewriting it, I'm going to actually just flip them.
Wait, how do you know that expression is in between -1?
In order for this thing to converge and have an interval of convergence, it has to be.
So just because the problem states that it has.
Because it's a geometric power series.
Right, okay.
And how do we know that a geometric power series has to converge?
How do we know that it's a geometric power series?
Because I'm multiplying by the same thing every time.
Oh, right, okay. No, I got it.
Okay, and we put it in this form to begin with. So, all right, so let's finish solving this. Okay, notice I flipped the inequalities, subtracted 1, that gives me -2, but then divided by -3, so that's my 2/3. Subtracted 1, that's my 0. Okay, so the interval of convergence is in between 0 and 2. And if that bothers you to have the inequalities and facing the wrong way, quote unquote, and having the bigger number on the left instead of on the right, like it is over here, you can certainly rewrite it. But these two, I mean, it's the same idea, right? Instead of 0 is less than x, which is less than 2/3. Or 2/3 is greater than x, which is greater than 0. It's just trying to say it's in between 0 and 2/3. That's the interval of convergence. Okay? Questions on that? All right, so this next example, we're going to jump ahead a little bit. We're going to go to example 5. Okay? So it says, using the power series from example 2, there it is. I wrote it down on this slide. Okay, so you can copy paste if you want. Make a new series for g of the square root of x. Okay? So all we're going to do here, simple enough, is we're going to substitute all the x's with the square root of x. Okay? And oftentimes we have sort of a base, and I'll tell you the term next week, or next week, what we call, we'll have this sort of base series, and we'll create other power series just by substituting it. Okay? So it is that simple. Right? Just substitute the square root of x in for x in G. And so when you get to your homework and it asks you to create a new power series with some other value, that's all you have to do once you have the original series that you're working with. Okay? So in this one, I would simplify it a little bit, and here's why. Since we're talking about power series, we want to have things expressed in terms of powers all the time. And if I can simplify that a little bit, I can. Since I have radicals, we're talking about rational exponents, and so what I would do is go simplify this a little bit, not much, okay, just to get me here. 3 plus x to the 1/2 plus 12x plus 24x to the 2/3. And again, it's about that pattern recognition thing. And when we can express it as powers, it's going to be easier to find that pattern if we had to go the other way.
My bad. That is 3/2, not 2/3.
Yeah, it's going to help us with that pattern recognition that eventually we're going to be doing when we go the other direction. Let's see if I can do this. That's better. Okay. Right, so half, 1, 3/2, 2, 5/2, 3, that kind of thing. All right, let's keep moving. So that's by substitution. We come up with a new power series just by substitution. We can come up with a new power series by differentiating. So we start off with that original power series that we worked on. I guess, yeah, we did. We had it as 1 over 1 minus x. So that was the very first example we looked at. What it's asking for is a power series for the derivative of f. Which means all we have to do is take the derivative of each of the terms. So the derivative of 1, of course, actually, why don't you go ahead and do that for these first few terms. Find the derivative of, okay? So hopefully that's what you got. 0 plus 1 plus 2x plus 3x squared, etc. Now, I understand that you don't quite get the reason why we're doing all this stuff yet. And that's a fair point, it's a fair question, because it just seems like, all right, we're going through all these motions of things, but why? Where's this going to get us? And on Thursday and Friday, I'm going to show you why, where this all comes from and what the application is of it. For now, what we're doing is we're just getting used to the mechanics of it, and then we're going to get into that deeper level concept. So let's look at another one. This is example 7. Here's j of x. Okay. So here's this series 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and etc., etc. Okay. Find j prime of x in the similar way that we did for the series above. So one of the things I'm seeing you guys struggle with a little bit is this factorial idea. This is 2. This is 6. This is 24. Right? And so what happens when you go to differentiate it, right? This 4 comes down and cancels with this 4, which leaves me with 6. This 3 comes down and cancels with this 3, which leaves me with 2. This 2 comes down, cancels with this 2, which leaves me with 1. Right? So what should happen when you integrate this, differentiate this? Here's what you get. This one just gives me 0, this one gives me 1. The 2 cancels, that gives me x. And let me write it out so you can see it. Okay, so this becomes, I'll go this way, 2x over 2 factorial. Goodbye. 3x squared over 3 factorial. Okay, so that leaves me with a 2, because that's 3 divided by 6. Then 3x, oh, I did that one already. If I kept going, which you don't have to, but it would be, oh yeah, you do, 4x to the 3rd over 4 factorial. Well, that's just 6. Well, which is 3 factorial. All right, and then I get my other terms, okay? What do we notice about the
derivative of j compared to j. It's the exact same thing. Okay? This really is 2 factorial and 3 factorial. My nth term is the same as the nth term. I guess technically I should. Well, what function do you know that its derivative and itself are equal to each other? E to the x. Okay. So j of x equals e to the x. That is the only function I think, off my head, that the derivative and its function are the same. Okay. So you got to be careful with the algebra, right? And so in some of your cases, maybe you do want to simplify these factorials out if you're asked to do that, so you can see the numbers more clearly and that they end up being the same. All right, we're going to keep moving because we still got more to cover. All right, let's look at integration of a power series. Same idea, you know, we're going to integrate each individual part, but we're going somewhere in particular with this one. So here we have this function 1 over 1 plus t. We looked at minuses before. All right, and this ends up being this kind of series. It's an alternating series. 1 plus 1 minus. If I integrate these terms, okay, and if I integrate with respect from 0 to x, it's essentially going to turn into a power series in x. But I'm just gonna put this up here because I don't want to run out of time. All right. So when I integrate 1 over a whatever, that's the natural log. Okay, in this case, it's the natural log of the absolute value of 1 plus t. And I'm going to integrate that from x to 0, from 0 to x. And of course, when I integrate this, I get t minus t squared over 2 plus t cubed over 3, etc. Okay? And so when I integrate it from 0 to x, I have to, of course, replace this with x and subtract when it's 0 and then evaluate from there. Okay? So this part is the natural log of the absolute value of 1 plus x minus the natural log of 1, which what is the natural log of 1? All right. So this whole thing just is 0. All right, so it kind of can go away. All right, and therefore, same over here, when I plug 0 in and subtract all these, well, it's just subtracting a bunch of zeros. That's why I don't have it here. All right. So the next thing we need to consider is these absolute values and if they're necessary. Okay, well, in order to find the absolute value in order to decide if that absolute value is necessary, I need to know what the values of x could be, right, to make sure this thing doesn't ever turn negative. This always has to be positive. Well, if I go back to my original function, what is r? No. Negative t. Okay? R equals negative t. Right? Which means that negative t has to be in between negative 1 and 1. Okay? Or negative x in this case after we plug the x in. So, x, this interval convergence, right, has to be in between negative 1 and 1. Well, does that ever make this negative? Do these values in here ever make this negative? If negative 1 in theory is the smallest value, which it can't be equal to, it's got to be greater than negative 1. But let's say it was equal to negative 1, then this would be 0, which would still be okay. No, it has to be positive, so that would not be okay. But so if I was a tick above negative 1, Okay, that would be smaller than 1, therefore this would be a positive number. Long story short, what I'm trying to say is once you find this interval of convergence, the absolute value is not needed anymore. Okay, because we guarantee that this value is going to be positive. Why is that important? Well, because I'm going to finish this problem up, maybe. Okay. And so I get the natural log of 1 plus x is this power series. And we're going to expand on that. Because while that's great, it would sure be nice to know what the power series for natural log of x is. We just looked at what the power series for e to the x is. As it turned out. You didn't realize that at the beginning. But that's what we did. That was the power series for e to the x. Now what we're going to do on the next slide is come up with the power series for the natural log of x. All right, and so I'm going to jump ahead, and I know this is going to irritate you, and I apologize. So essentially what we're going to do is I'm going to replace the x's here with that 1 minus x that we just put in that place of x. So this program likes to autosave, and it's taking so much longer to autosave, right? So here's what I'm talking about. You can fill it in there, okay? So we're going to use this to come up with the natural log of x power series, right? And essentially what I need to figure out is, since we did on the last problem, we found it as 1 plus x. What we want is that 1 plus x to just equal x. So we have to figure out what can I add to that 1, that substitution like we did originally, to make it just equal x. Okay. And so there's, again, that little algebraic manipulation is just plugging x minus 1 in, right? Because 1 plus x minus 1 is x. And so what I can do now, in that last problem, I got it in that form again. In the last problem, I had it as natural log of 1 plus x. What we're going to call our x now is this x minus 1. So we're just going to substitute that in the last problem. Going to end up looking like this. So this is the form that we used on the last problem. And so essentially what we're going to do, and I'll go back to it really quick. Come on. Okay. So instead of having the x, I'm substituting the x minus 1 in wherever there was an x. So this is the same function that we just did for that previous example, but instead of it being x, we're substituting x minus 1 in. All right. So that's how we're going to use other power series to generate new power series, ones that will eventually be more useful to us. And then the last little example that I want to talk about is this example 10. Okay, so now it's saying, okay, fine. You came up with the series for natural log of x. Good job. Now come up with the series for x squared natural log of x. Well, that ends up being pretty simple. You take what we already had and multiply it by x squared. So, yeah, we're not going to simplify this. We're not going to multiply it out or anything like that. But we want to get in the habit of looking for some of these patterns and how to use things that we already know to use with things that we can discover.